Okay, so some of you may have noticed that we've done some rearranging of the schedule to improve the schedule. And so this will be a little connected to, I think, to Luana's bootcamp yesterday, more about random graphs and GNNs. And I'll turn it over to you, Yeganeh.
Yeah. Thank you for having me. I hope you're not disappointed by the change of schedule. My name is Yeganeh Alimohammadi. I was a UC Berkeley president postdoc up until like a few weeks ago. Now I'm an assistant professor in University of Southern California in the School of Business. And this is joint work with my fantastic collaborators, Luana, Ruiz. I don't know where she is now. And my PhD advisor, Amin, Saberi. And this talk is going to be like half bootcampy and half like talk. And I have enough time to answer as many questions as you want, so feel free to jump in whenever you want. Well, like it goes without like saying in this audience, but just to set up the stage, a lot of modern applications of networks are large scale, which includes recommendation systems, social networks, knowledge graphs, that the range of node size and like edge sizes goes to even like billions of nodes and edges. And GNNs are the main tool that enable these large-scale network analysis. And we already learned yesterday about like message passing based GNN, but I'm just like going to like do a recap for the completeness, and which is the main focus of these talks are the message passing based GNNs, where we learn embeddings of networks via message passing between neighbors. So what do I mean by it? I have, for example, a graph here, the node 0 and its 2-hop neighborhood. And the way that it works is that node 0 gets messages from its neighbor, like 1, 2, 3 here, and aggregates it with its own information to get the message for the next layer. And this is also happening for the other nodes. So like node 1 is getting information from its neighbor, which is 0, 4, 5, 6. So there is, to set up the notation, there is like edge of U. U is the node of layer L, and it's some aggregations happening here. This can be something simple like the mean, and then then we're combining this aggregated message with the node V, node 0's message, by something that can be like ReLU, which is an activation function. And here the parameters that are learnable, I'm showing it with W. Okay. And as you can see, like as you can imagine, as I increase the number of layers in these message passing based algorithms, the size of this computational graph, which is on the right, is going to grow exponentially. And that's the main challenge when I have large scale graphs, that I cannot just do full batch training because just the sheer problem that I have like in the computational limitations in the hardware, let's say. And traditional methods like stochastic gradient descent doesn't work here, because if I have a sparse graph and I'm just randomly choosing some nodes to learn from it, it's going to give me isolated nodes mostly, which is not like taking advantage of the graph structure that I have. And with that, instead of like doing SGD, like the solution that has been like done in practice is like use the graph and graph sampling to basically make the training sizes manageable. And now I'm just like going to give you like a brief overview of what different graph sampling that have been used in practice before telling you what is our objective here. So I'm going to use like this like pictorial ways, like show it. So I have a full GCN result. For example, I have for this small graph, I turn it into this full computational graph that, for example, node 6 is getting information from its own, and node 4, and then node 4 is getting information from all to 6, which is all of their neighbors here. And even for a small graph like this, I can see that the computational graph is like kind of already complicated for a board. One class of algorithms that make training scalable for GNNs were node sampling algorithms, which came out starting in 2018. They do graph stage and pin stage are like one of the famous ones that came early in 2018. They do, for example, random walk-based sampling. They start, or some other sort of neighborhood sampling, that they start with a node, and at each hop, I'm subsample some of the neighbors that I have. So for example, I start with node 0, and I'm sampling like 2 of its neighbors. It turned out to be 0, 1. And then I sample 2 of the neighbors of 1 as well, and I do that to like make my computational graph manageable. And here, one thing to note is that, for example, node 2 got sampled twice, but I kind of forgot that there were like 2 copies of the same thing here. Then another class of algorithms that came out were layer-wise sampling, which took the whole layer of the computational graph in mind when they were like sampling. So again, the difference here is that like I had the whole layer in mind that, for example, one node could appear twice, and then doing the sampling here. Again, this could be like fast GCN, which is importance space sampling, is one example. It could then be adaptive sampling GCNs or other methods. Okay, I'm just showing very few of the examples of the whole literature here. Yes?
So in node sampling, this is an iterative, a recursive algorithm. I sample from let's say a node that I'm interested in.
Yes.
And then I sample from the nodes that I've created in the sample.
Yes, yes. Exactly, yeah. Then a third class of general algorithms are subgraph samplings that I take into account my whole graph. For example, I cluster them into smaller graphs and then feed those small cluster as like the whole input to my GCN and make that smaller graph into like embeddings. And as I said, like clustering as an example, cluster GCN is one of it. There could be like GraphSend, which is like random bucket-based sampling of the whole graph. And even like newer methods that are based on other scales, like tree movers distance. I know there are new works like by Ellen and Stephanie and Luana on this too. And of course, there are some other methods that doesn't fit exactly in any of them. So for example, I know by people in the audience, there are methods that are based on rewiring of the graph that like subsamples and then rewire. But then here I'm only focusing on methods that keep the first structure of the graph and subsample from it, right? To kind of summarize the different graph methods that are based on sampling, I can think of it as like this high-level like view that I have a graph G as data input, and then I have a graph architecture that have 3 versions of sampling in mind. So like there is mu-S, which is subgraph sampler, nu-G, which is node sampler, and a layer sampler nu-C. Then based on this, it creates some node embedding, and there is a loss function of your interest that compute the loss for this node embedding, and then train the parameters WT that I have. If the gradient of the loss is small enough, then I finish and I'm good, and otherwise I do the same loop again. So kind of like this is the high-level pictorial of different sampling-based GNNs. And if I choose these like samplers, if I choose them well enough, then I can recreate a lot of these like sampling-based GNN that I was telling you have been working empirically in practice. Okay. So like so far, I'm just like telling you about what has been happening for like training GNN and scaling them. But what was the main objective of our work, which is that we've observed that GNN scale well, but is there a theoretical framework to unify the study of like how sampling-based GNN work? And second question, and the main one, is that when I'm trained my sampling-based GNN on a small subgraph, does the parameter that I learn give similar kind of loss that I get on the whole graph as well or not? Okay. So these are the main questions, and I tell you our result in a very high level first, and I get it like into more detail next. Okay. So at high level, we show that training a large enough sample size give us parameters that if I use the same parameters on the full graph, I would get the same loss function. Okay, this is like very high level, but the main assumption that I have, which I'm going to like define it very clearly next, is that the loss function and the different samplers that my sampling-based GNN is using are local. And right now, I'm just like telling you all like, it's not yet precise, but I'm going to like to spend some time on what does it mean for it to be local, right? Any questions so far? I just pause for a second. Okay, some implication of this result after I formalize it would be that It applies to many of the GNN architectures that worked in practice. Example of them are some that I mentioned first. Basically, anything that has like this sampling algorithm as a local function. The local function can be something that's like depends on the spectral properties of the graph, but is approximatable by local characteristics of the graph. Second thing is that it relates to the transferability, which actually is what Luana also talked about yesterday. So like it relates to this whole literature of transferability that like performance on large graphs can be described by the smaller subgraphs. And the third thing is that if I have a large scale graph and I don't know which architecture to use, maybe I can just use this like idea that small subgraphs give me enough approximation of the loss function to compare different architecture fast, and then like go and find the right hyperparameter for the larger graph, which takes more computation. Okay. With that, I'm going to like, if there is any questions so far, let me know. Otherwise, yes. Yeah, the last point I meant by that what we're going to show is that basically if I just use a small subgraph from my input graph to train different sampling-based GNN, I get similar loss as I would get if I had like trained it on the whole graph structure. So I can just use that as a proxy for approximating like how well a GNN architecture is working on this data set or not, and then like actually going on the full graph and like use all of my computation or however to like take the data. Yeah. Yeah, so like the convergence rate and how well actually how small the graphs are depends on the algorithm, but in general, like at least asymptotically, most of them would give you constant size. Yeah. Okay. Now I'm going to like have a detour of like telling you what local means, and for that I need to define local graph limits, which is a theory that has been developed well in probability theory. Okay, so this is in a box now outside of it. So basically, local graph limits are providing a theoretical framework to relate local graph structures into global properties of it by defining a metric space on objects that we call limit graphs. And this is a theory that has been developed more than 20 years ago by Benjamini and Schramm and Aldous and Steele, and where we say, like, in a high level, a sequence of graphs have a limit if the empirical densities of the local subgraphs converges. This is like, I know that Luana already talked about graph ones. This is like a sister of the graph ones for a sparse graph data set, which gives you different characteristics of graphs, especially if your average degree is constant compared to the whole graph. Okay, I'm going to tell you with examples what do I mean by local, like what do I mean by limit graphs, which is some small examples next. So I start with the simplest graph structure, which is a path. And I want to see what would the limit look like if I increase the size of the graph of a path, okay? The way it works, the way I have to think about it is that I choose a uniform random node. I show it with orange. And then look at a fixed ball of a radius around it. And here I choose like ball of radius 1. And then see what's the subgraph frequencies I get. So simple. Every time I choose a different uniform random node, I see the subgraph. So for the radius 1, with probability 1 minus 2 over n, I see the path of size 2. With probability 2 over n, which is the endpoints, I see the path of like length n. As I increase the size of the graph, I basically just see the first one. And as I increase the radius size, I basically see an infinite path, which is like rooted at one point, okay? So this is going to be my limited structure if I just have a path. Okay, this was just like a warm-up simple example. Another simple example to give you more idea is that let's say I have a grid with like this cross.
So in the previous example, the radius was independent of the graph size.
Yes, so you choose like, the final graph is going to be infinite, and the radius that you choose is like going to be any constant that you want. Right? And then now like another example to give you like more idea is that like I have this like grid with like crosses. And as I increase it, I want to see what's the limited structure is going to look like. Okay, if you look at it a little bit, I have two types of nodes here when I choose a uniform random node. It's either like these middle nodes that have like degree 4, or like the nodes that have like degree 8 and so on. And if they're not in the boundary, their local structure of these types of nodes all look the same, and these types of nodes all look the same. So the limited structure is going to be a probability over two types of graphs, like two types of rooted graph, with probability half I'm lying here when I start with a degree 4, with probability half I lie there. Okay? And again, these are like simple examples just to give you ideas that the limited structure is basically a probability measure over all like infinite locally finite graphs. And the way that this theory works is that it actually formalizes viewing of graphs as this infinite structure by defining a metric space over all these like infinite locally rooted graph. The metric space in a high level is that like if you have two rooted graphs, G1 and G2, these are like roots, then the distance of them is basically inverse of the furthest ball that they are isomorphic to each other. Okay, it doesn't matter like to get the details of it, but the nice thing is that basically there is a theory, I get to in a second, that like there is a theory to like make the topology of these like infinite graphs like Polish and separable and all the nice things that you need to learn about it. Yes.
What does local metric mean? Is it just a name, or?
Oh yeah, this is just a name. This is just a name. Yeah, it's just local because it says that up to like a distance locally they're isomorphic. Yes.
So the rooted graphs that come because you're looking at the vertex around it?
Yes.
Okay.
Yeah. Yeah, so like your original graph is not rooted, like the ones that are finite, but then the way that you define probabilities on it is that you choose a uniform random node every time you like look at it locally. Yes. There was another question, I think. Okay, no. Okay, so the formal definition, with now that you know like the metric and all, is that a sequence of graphs converge locally to a probability distribution on the space of all infinite graphs G star. If for any rooted graph, the density of H in these smaller graphs is converging to the density of H in the infinite version of it. Okay, and yeah, so like because the metric space mu is a well-defined space, you can define like convergence in probability and distribution almost surely. Basically, it's the same as like asymptotics that you have for random variables, but now for graphs. And another thing to say is that the theory for it, the first version of it was just for graphs without any marks, but you can easily extend it to when you have like attributes and like features and on edges and nodes. Okay, and another thing I wanted to say is that like all of the sparse random graphs that you know have a local limit. It can be geometric graph, hyperbolic geometric graph, like stochastic block model, anything that you know that's like sparse being the average degree is constant, has a local limit. So you can just, instead of proving theorems for a specific random graph, you can just prove it for graphs that have a limit which just applies to all of them. Now I get to defining the assumption that we have, which was that we needed the samplers to be local. Formally, a function is local if for any convergent graph, so any graph that has a limit with the sense that I told you, the function on these like a smaller graphs, its expectation over random nodes that I pick converges to the expectation on the infinite version of the graph. Okay. Maybe I give you like some examples of it so you get an idea. Basically, random walk samplers or random walk centralities are one example of this like local function. If I choose a uniform random node and do a random walk and see where I end up, it's going to give me the same distribution as I do it on the infinite version, right?
What is this G star to the n?
Oh yeah, G star. So here G star is like the space of all rooted graphs. And then n means like it can be like you can have n different roots. So like instead of like one root, you can have many. That's useful for example, when you have negative sampling. You need like a few different roots to like compare them together. N is fixed here, yes. Yes.
So the k should be an n. And third line.
K should be, oh yeah, this should be N, sorry. Yeah, you're right. Yeah. And then,
Sorry.
yeah.
You said K should be an N, but it's not the same N as that GN.
Yeah, this is the size. The small n is the size of the graph. This is like the number of roots I choose in the graph, which is fixed. Yeah. And then
capital N.
yeah,
K
capital N. K should be capital N. Yeah. And another example of this is like when I basically sampling with respect to like importance sampling in the terms of, for example, it can be the inverse of adjacency matrix like the Laplacian and so on. Those are also local functions. It can be locally approximable.
Sorry,
Yeah.
but this mu is not fixed here.
Mu is a distribution over all like finite, infinite graphs.
So there's
right?
it's not a mu almost local function. It's almost local if for every mu,
Yes, for the functions. Yeah.
for every mu this holds.
Yes. Yeah. Mm-hmm. Yeah. And there is like a whole literature on like basically, for example, proving page rank is a local function or like clustering coefficient is a local function. And in our paper, we have to show that negative sampling and like importance sampling when we have like Laplacian as like the scores, then it's also, those are also local functions. Okay, maybe just like the one vertex version of it is easier to think of. Like I have a GN and a vertex V1, and I define the function of GN and V1. So this can be like the page rank of V1 in GN. And I want that expectation to convert to the expectation if I had the whole graph. Like this is what it means. I can also remove the expectation and think of it as like distribution, like convergence, right? One last thing about the detour is that there is a whole literature on just like studying local graph limits. One is like studying like local graph properties on average, for example, like the maximum matching in a random graph and mini-spanning tree, k-core, max independent sets are local. Or studying like random processes on graph, for example, information cascades, we know those are local, which helps us to like estimate them with just like local information of the graph. And also, like, there's a lot on like combinatorial optimization and interactive particle systems. So I'm just like citing two things. One is like a survey on the applications of the local convergence and their application. The second is a book that has like a lot about the theory of it and like anything that you need to have the technical tool to use it. So this is all I wanted to say in the detour. If there is any questions about this local graph limits, let me know. Otherwise, the detour ends here. Okay. So now I tell you the main result with this like more formal structure. I have consider a sampling-based GNN. I use A for it, and then I have this sampling-based GNN has almost local samplers and almost local loss function. And then also I'm assuming the loss function is Lipschitz. Then I have the input graph, which is coming from this infinite version of limits from mu. Then we show that for any epsilon, there exists an epsilon, which is independent, it's a constant. So it's independent basically on the infinite version of the graph that I have as a limit. We show that training the sampling-based GNN on these samples of size n epsilon converges to the epsilon neighborhood of training it on the whole graph. So basically, if I take the expectation over the gradient of the loss function, where WT is my training parameters on the small samples, the loss function is going to be bounded by this epsilon as well. Then also I can bound the number of graphs that I need in this first part by 1 over epsilon square. That's like the general theme of the result. Okay. Yes.
Quick question. So for example, does the local loss function, for example, if I were to train for no classification problem, so maybe the loss function will just compare my predicted node unstable versus the true one. So
Yeah.
does this satisfy the assumptions?
Yes, that satisfies the assumption. You can also, like in your loss function, you can also have negative sampling in terms of like, for example, if you're like looking at edge labels, you want to like have positive and negative, then that's also basically like as if like you're adding another root to the graph, and that's still fine. Yeah. Yeah. So basically, like again, like these assumptions that we have on almost local samplers and Lipschitz function applies to a lot of these like basically sampling-based GNN that I like listed some of them here. Okay. I spent like maybe, if there is any question here, I pause for a second. Otherwise, I spend a few minutes on some proof ideas. Very high level. Okay. So the main proof idea, I'm just like going to like separate it in 2 steps. The first one is that an informal lemma that I want to like compare the gradient of loss on the finite graph with the gradient of loss in the infinite version. So this is, WT is like the trainable parameter for fixed T on the small subgraphs. And then I want to see what would happen if I have used that same parameters on the infinite limit that I have. And the first part of the proof is that this converges to 1. And this is basically where like the local graph limit theory comes into place. This first lemma is just proved because I am assuming that the samples that I get are from the general families that have this infinite graph mu. Then the second part of the lemma is that, well, like just knowing the gradient being the same is not enough. I also have to prove that the loss on the infinite version of the graph also decays as I'm changing my learning rate eta. And this is the second part that we're showing that the expected of the loss of the discernible graph for the infinite graph is going to decrease in each step by at least a constant, let's say. So putting the 2 together, if I know that this expectation is more than epsilon, basically my algorithm would stop when the gradient of the loss on the infinite graph is smaller than something. And if this expectation is more than epsilon, I know that at least in each iteration there is a decay by epsilon times the learning rate. So like the number of steps that I have to go is going to be proportional to 1 over epsilon squared, basically. That's like the general high-level idea. Okay. Any questions so far? Okay, I want to just show you some experiments before like finishing the talk, which is that, so this is an experiment on PubMed dataset with 20,000 nodes, and where we have like 7% of the nodes to compare 2 different GNNs. So one is the graph stage, and the other one is the GCN. So here, like the dotted thing is when I have the full graph, and the solid lines are when I'm using sampling. And remember, one thing I was saying was that like this framework of just like sampling can be helped to like get prediction of the loss function on the whole graph. Is kind of showed here that like with sampling I almost get the same loss that I get on these like full graphs when I was not using sampling, basically. And okay, I finished with like some takeaways. Is that basically like the main theoretical takeaway is that small samplers are sufficient to estimate the loss of most GNNs, most sampling-based GNNs. And the second thing, which is I think what I hope this like audience also get more engaged with, is that graph limits offers like a natural framework for analyzing GNNs, because graph limits are a way to like understand local graph structure, which is basically what GNNs deal with when they're working on it. And with that, I just like have a few open questions before finishing, which is that what would happen if we have adaptive sampling? So in our framework, we are not using with the sampling. When the sampling depends on the loss function and it changes in each iteration, we don't know how to deal with that. So one question is like, can we make a framework for analyzing them? Second thing is like for dynamic graph, where by dynamic graph I meant like, for example, the graph structure, the edges are like rewiring in each step. The newer theory of graph limits, which is like only less than a year old, can now deal with like dynamic graph structures as well. But I don't know like how that theory yet can be applied to when we have a GNN learning on the dynamic graphs. And another one is that can we use the understanding of graph limits for constructing new GNNs that maybe work better than the previous ones? And with that, I'm going to stop here. Take any more questions you have. I know it's a early stop, but I hope that like it works well with the launch schedule as well. Thank you. Yes.
So it maybe relates to the question from the back. If I wanted to get insight into how large my samples need to be, would I get what you know about this?
Yeah. So this first lemma is where I provides like how large the samples need to be, like the gradient of the loss on the small graph versus the full graph. And generally, it depends on if I have to give you a crude complexity, it depends on the distribution of the neighborhoods of the original input graph, in one sense. So if it's like very regular, it's going to be small sample size. But if it's like more skewed, it's like then you need more samples to get like some ideas of like the parts that are like basically have fewer density in the graph.
So there would be some metric that I could, of regularity, that I could give you. My graph is,
Yeah, so like
0.7.
Yeah, so like if you give me the distribution, if I have an idea of like this distribution.
No, but I'm saying, of course, I cannot give you a distribution.
Yeah, right.
So if I just wanted to give you some statistics, you could use this to estimate how many samples.
Yeah, like there can be a way to think of it like that. It's not like a.
I give you, maybe the first few moments.
Yes,
about
yes, that could be like that could give me a crude upper bound. But like a better bounds would depend on the GNN structure as well. If the GNN is like basically subsampling itself, like it makes it, I may need even like less sample because it's kind of regularizing the graph in a way.
What do you mean by the GNN is subsampling?
So like the GNN architecture, for example, if it's like doing some if it's a graph stage, yeah, then it's already changing the structure to be like more smooth in a way.
Okay.
Yeah.
So here you're showing, for example, the main idea is the sample graph kind of is unbiased. It would be sort of like an unbiased loss function.
Yeah.
And I know there are some samplers that have some extra objective. For example, they want to minimize the variance in the subsample batch or whatever. So maybe can you comment on if there are, let's say, like other aspects of the sampler that can be used to like derive maybe sharper results, or like you thought about analyzing them?
Yeah, like for example, variance reduction GCN is one of them.
Yeah.
I've thought about it, but our theory right now doesn't work really because the sampler there like depends on the loss function every time it's changing, and I honestly don't know like how to deal with that. Like when you have a sampler changing based on this small subsample and compare it to the full graph.
I see.
But I think it's a very interesting question to look at when you have this adaptive kind of sampling. Yeah.
Thank you.
Yes.
So in the definition of your limits of graph limit, it has to kind of match with any possible subgraph of a certain size, right?
Oh yeah.
But when you're looking at GNNs, like they cannot distinguish between certain subgraphs. So isn't it sufficient to make a definition where you only want to match like graphs which are actually distinguishable by GNNs? I mean, it seems to me like the limit is too strong for the GNNs.
Yeah, so like that's a good point, but it's too strong, for example, when your input features are uniform. Like here, the way that I showed it is like I don't have the features even like in this type of definition, but if my features are also random, then I think it's like more specific.
Unique. Okay.
Yes, and you have, so like in that case, then you need like the more evolved version of these like graph limits to work with it. we don't assume anything about the input features. It's just like coming from distribution that depends again like on the local structure.
So, but you need input features.
You can have input features, or you can yeah. We don't need an input feature because basically, okay, like again say the results again. I'm not saying how expressive are GNNs. I'm just saying that the GNN, the way it works on the full graph is the same way it works on the subsample. So if the full graph had feature, your subsample also had some features that is like representative of the full graph.
Yeah, we can take maybe offline. I think I was more thinking maybe the definition of the graph limit can be weakened because GNN is weakened and yeah.
That makes sense. I think I didn't think of it that way to make the least sufficient kind of definition. But yeah, that makes sense to like think of it.
I don't know if it's related, but it's also striking that so a lot of details of the GNN architecture don't seem to be very important for this. So if I just compare with Pablo's talk, there is a lot of this seems irrelevant. Like what sort of activations you're using is not important for this result.
Yeah, I like need that is the loss function to be local. So like it's locally approximate. It's fine if it's like nonlinear, but as long as it's just using the local information of the graph, that's all I need.
Yeah, somehow quite surprising to me.
Well,
and it's, if I had like a global readout, this also doesn't make a difference.
But like global readout is making a difference because then that depends on the whole structure. Yeah.
So any kind of local GNN is okay.
Yes,
basically.
exactly.
So,
yeah. Oh yes.
Have you tried using local global convergence to get maybe a larger set of functions that you can play with rather than just local functions?
Yeah, so like one thing I kind of pushed under the rug was that, for example, like any function that's locally approximable, you can use this local to global kind of results, like show you can use it. So for example, when I was saying you can use importance sampling where the scores are like, for example, Laplacian or inverse of a Laplacian, they're not directly local, but they're locally approximable. So like that's like a way kind of answering. Wherever you can prove that like there is a local to global connection, then you can use this theory. Basically, yeah. Oh yes.
So is my understanding correct that when you talk about the local limit, essentially the degree has to be bounded and not grow within? But this, when you talk about function as this local, what you call almost a local function, it actually is independent of that.
Yeah. So the degree, max degree is okay. It can like grow with the size of n. But the average degree should be bounded, or more precisely, when you choose a random node, with high probability, the local structure should be bounded. Yeah, so it's not exactly like bounding max degree, but it's bounding the average degree.
I see. So is there a way to somehow make this a little bit more general so that it can also handle graphs where the degree grows with n?
Yeah, that's a great question. So like that's like
because for the almost local function, it actually does not need this.
Yes, but there is like the local graph limit that I told you here. What is developed for sparse graphs, but then the graph ones that Luana talked about is developed for the dense graph. So these are like two different kind of like views of like seeing graphs as a limit and asymptotics that can be used. So in your question, you should probably use like graph.
Whether you can kind of integrate them together.
Yes, there are like also like versions in between like graphics or like that are, for example, like the average degree is log n, for example, but the theory is different because the way that you define probability will like change how you see the graph. It can be trivial if you like define it the same way as you do it like on the dense graph. Thanks for the great question. Okay, it seems like.
Thank you again.
Thank you so much.
Reconvening at 1:30.
1:30, yeah.